Hi everyone. So today we are done with functional analysis, and we turn to geometry. So I'm going to present this curvature theory for Markov chains. Again, even if you don't care about cutoff, this is a beautiful theory that I think is really worth knowing, and it's used everywhere. Okay, so the word curvature, I'm sure you have heard about it. It comes from the Riemannian geometry of the study of manifolds. Right? It's called the Ricci curvature. And it's a notion that plays a key role when you study manifolds. The term appears, I guess, in every result in Riemannian geometry. You have the word curvature somewhere. Right? Curvature is really what you want to know about your manifold. It really allows you to say many nice things about the manifold. And the theory is so powerful that people recently have tried to make sense of a notion like that in the discrete world, and try to see if those amazing results that are true for manifolds also work in the discrete. Okay? So it's very much research in progress. It's a very interesting field of research where you basically, first you have to come up with a notion of curvature that works in the discrete. And once you have done that, you can take every classical result in Riemannian geometry and try to write down a version of it in the discrete. Right? So it's a fascinating topic. And what is interesting in this discrete world is that it's not actually clear how you would define curvature. There are several ways to do that, and they are not equivalent. Right? So there are several notions of curvature. I will describe the two simplest one to you, the most useful in my opinion. But there are others, and if you care about that, yes, just look at discrete curvature on Google. You'll see that it's quite an intensive field of research. Okay, so today, the simplest possible notion, I guess, called Olivier-Ricci curvature, and which is based on optimal transport. Okay, so this is taken from, at least the start of the lecture, is taken from a survey by Yann Olivier from 2010, where he really starts with Riemannian geometry and then moves progressively to discrete state spaces, and he makes a lot of nice connection between the two worlds, and also he states a lot of nice conjectures about results that are true in the Riemannian setting and that should also be true in the discrete. So I really encourage you to just leave the room and go and read this survey by Yann Olivier. It's very nice. That's where I learned everything from about curvature. Okay, so the basic idea is that I'm not a geometer at all, as you can guess, but one way to view Ricci curvature is using geodesics. Right? You can take two, for example, on the plane on a flat manifold. You take two starting points nearby starting point, and then you send. You look at the geodesic in parallel directions starting from those points. And you see that on a plane, nothing very interesting happens. The two trajectories, they remain at constant distance from each other. Now, if you play the same game on a sphere, which is an example of a positively curved manifold, right? So maybe you have your point here, and then take another point here and send same direction. Well, actually, the distance on the sphere will become closer and closer until they actually meet, right? If you somewhere at the North Pole, they will coalesce, those two trajectories. And finally, on a hyperbolic manifold, so this is a terrible drawing, but if you just Google image hyperbolic manifold, you'll see much fancier pictures. I cannot draw them, so that's my way of picturing a negatively curved manifold, but it's really not what it. Don't take this as a serious picture. But here, you take two geodesics starting parallel, and then you see that they actually diverge. So we'll do like that. Okay, so that was the starting point for Olivier's definition of curvature. This idea that when you look at the geodesic, either they stay at the same distance, or they get closer to each other, or they get further away from each other. Okay, so he came up with a definition of curvature that works on any metric space. Right? So if we want to apply that to our Markov chain, we need to view the state space as a metric space. Okay, So you can choose any metric that you want. For simplicity, I will stick with the one I presented a few lectures ago, but really what I'm going to say works for any distance on the state space. So here, I'm going to assume, because I want to use this specific distance for simplicity, I'm going to assume that my diagram, the graph of my Markov chain is undirected. So which means that whenever you can go from x to y in one step, you can also go in the other direction. Okay. So this is of course satisfied for every reversible chain, for example. So it's not a big assumption. And again, even if this is not satisfied, you just change the metric and you can still make the theory work. It will just make my life simpler. And also I'm going to abbreviate this by just saying that x is a neighbor of y. And now this is a symmetric relation. Okay. And then I can define a distance on the state space. It's the one you have already seen before, right? It's just the number of transitions that you need to make in order to go from x to y. Right? So in terms of the transition matrix, just the minimum n such that the corresponding entry of the matrix is positive. Okay, so it's a nice distance on x. Okay, and now I'm going to use optimal transport to lift this distance on x into a distance on probability measures on x. This is the Wasserstein distance between two probability measures on the state space. Right, so now those are in the set of probability measures on x. Okay, and to define a distance between those two measures, I'm going to use this distance between points. That's the only knowledge I have. Right? And what I'm going to do is, so those are measures. I know how to measure distances between points. So I'm going to generate a random point according to mu, generate a random point according to nu, and then look at the distance between them. Okay. So this is all I can do with this object here. Okay, so this is a random quantity. It's not very nice at a distance, so I'm going to take expectation, get something deterministic. And this is still not very satisfying because this strongly depends on the way in which we are going to choose the random variables. Right? Here I'm only specifying the marginals, but you could couple those two variables in many different ways. And actually, I'm allowing to couple in any way you like, so as to minimize this quantity. Okay, so that's the Wasserstein metric. It's a very general way to construct a metric on probability measure once you have a metric between points. Okay. And it has several nice properties. I'm going to discuss that now, but one easy exercise is that this is actually a distance on the set of probabilities. Okay, so here I'm using this particular distance, but this formula works for any distance, and it's important to keep that in mind. Okay, so here are a few nice remarks about this. So the first one is that I'm saying that this Wasserstein distance is a way to extend any distance between points into a distance between probability measures. It's really an extension in the following sense, that if you look at Dirac masses, in this definition here, right, then you really get the original distance. Okay, the second important quantity is that I wrote this as an infimum, but everything is compact here, and so there is always an optimal coupling. Right? And I'm going to call any coupling that achieves this infimum, I'm going to call it an optimal coupling. Okay. So there always exists optimal coupling. Okay, another important remark is that in this W1, this is specific to this W1 metric, but we have a duality formula. Right? It's an optimization problem. You have seen in the other course that there is always a duality when you want to minimize it. You can also write it as a maximization problem. And then the dual expression. So this is due to Kantorovich, but it's really a specific case of this general duality in convex analysis. So you can also express this infimum as a supremum. I'm not going to use it, but it's for the intuition, I think it's good. That this is also the same as comparing integrals. You are measuring the distance between mu and nu by just looking at test functions. And then you take a supremum over all functions that are Lipschitz. Okay, so I have a metric space, so Lipschitz makes sense, right? It's just Lipschitz less than 1 means that whenever you traverse an edge, the difference in terms of f is at most 1. Okay, and the last remark is that I can play with the choice of the distance here. In particular, I could take the most stupid distance you could think of, which is the distance where every point is at distance 1 from each other. Right? So replacing our particular choice with the trivial metric. Again, that's a stupid choice to make. Right? So the trivial metric is just an indicator that the 2 points are different. If you do that and apply this definition, what you get is total variation. Right? Okay, so in a sense, you had already seen this Wasserstein distance in the first course, but the idea is that if you want to study total variation distance, it's very poorly behaved because this choice of a distance is not very interesting. And the entire idea behind this Olivier-Ricci curvature is that if you start to use distances that really take into account the geometry of your state space in a better way, then you should get nicer results in terms of behavior of this under the semigroup. Okay, so that's the idea. Okay, in particular, a consequence of that is that because this distance is always at least the trivial one, okay, this is always at least 1 unless x is equal to y, then you get an immediate comparison between this one and total variation. You are taking an infimum. In both cases, you are taking infimums over all possible couplings, but here, what is inside the expectation is always larger for Wasserstein than for total variation. Right? So you have a bound. Okay, so let me rewrite this now. And if you remember, when we started doing functional inequalities for Markov chains, the starting observation was that total variation distance is not good in terms of behavior under the semigroup. And so a general strategy is to replace it by something that is larger but better behaved, and then try to understand how this new quantity evolves with the semigroup. Okay, so that's again what we are going to do here, but no functional analysis, just geometry. So once you know this, once you realize that this is a particular instance of what I mentioned before I think this general metric I denoted like that. Right? Okay, so this was the first step of a general recipe where you try to estimate how this evolves with the semigroup. So this motivates the following definition. The Olivier-Ricci curvature of the chain is the largest constant such that you have exponential decay of this quantity under your semigroup. So you apply your semigroup starting from mu and starting from nu, and you want this to behave like that. Right, there is a 1, there is a 1, and this is true. You want this to be true for every time and for every measure. Okay, again, it's very natural in when you remember the general recipe I outlined before. This exponential decay is also natural in terms of the semi-group property. Right? It's typically something you expect using the Markov property. Okay, and if you are more a functional analyst, you can use this duality to express this in the following way. It's the same as saying that you want the Lipschitz norm to decay exponentially under Pt. Okay, for every t and for every function. Okay, and if you remember my story about the geodesic becoming closer and closer or staying like that or going further away, right, that's a way to picture this. Okay, so be careful that just like for manifold, and unlike what we did before for variance and entropy, this is in general not decreasing with the semi-group. Right? So this number k could really be negative. In this case, I'm always talking about exponential decay, but it's actually, if k is negative, this is exponential growth. Right? So be careful. K can be negative, just like in the Riemannian world. And I'm going to give example later. Okay. Okay, so there is no reason a priori that this distance decays under the semigroup. Okay, and of course, if you want to study mixing times, this is only useful when k is negative, when k is positive. You remember my general recipe. The first step was choose a distance that is larger than total variation but better behaved. The second was prove exponential decay for it. And the third was just get the nice conclusion, which is this mixing time bound. The general formula was 1 over k, and then we had log of maximum value divided by epsilon. So here we get the maximum value of this is just the diameter. Right, it's a stupid observation, but this Wasserstein distance is at most the diameter. Okay, so using this exponential decay plus this relation, you get this. Okay, you also get a bound on the relaxation time. Right? Remember that the relaxation time is tells you how this decays at large time, and this gives you exponential decay at large time. So you know that this spectral gap, this lambda parameter, is at least k. Right? Right, this was the spectral gap from the first lecture, and you know that it's at least k. So you get an estimate on the mixing time and on the relaxation time. Right? And let me remind you that this spectral gap is the same as the Poincaré constant. That's a lot of Greek letter, I'm sorry. Which I denoted gamma or gamma optimum when your chain is reversible. Okay, another way to view this is to picture the fact that this curvature controls the spectral gap is just you take an eigenvector here. You take f to be an eigenfunction, and then you get this relation. Yes?
Just a question. If you wanted to define this notion of curvature for a general metric space, what would be the semigroup that replaces the...
So yeah, that's his point, that you need a bit more than a metric space. You also need, at each point, a sort of a transition matrix, or a way to associate to each point a measure. And what he says is that in geometry, it's very natural to do that. You have a point, and you take the uniform measure, you have a point, and the equivalent of the distribution after one step starting from X in a general metric space is take the uniform measure on a ball of radius 1 around X. Right? So in any metric space, you can take this choice as of a transition matrix, right? Take the uniform measure on. And when you let the radius go to 0, you recover this Ricci curvature theory for manifold. So it's really a nice extension of this Riemannian geometry to the discrete world. But again, it's not the only choice.
Sorry.
Yes?
Is it obvious that the two formations are equivalent? I mean, in one direction.
This one and this one? Yeah, you are totally right. So it's always like that. My feeling in duality is that it's always like that. One direction is obvious, and maybe I'm going to prove the easy one. And the other, in duality, the other direction, even in this equality, right? There is one inequality which is always clear, right? It's this one. But proving the other is really some abstract duality thing that is not totally obvious at all. But I mean, once you agree with this formula, then this is really clear, the equivalence. Yes. But proving the equivalence here is... Anyway, we are only going to use this direction. Throughout the course, I'm going to use this, and this is easy to prove. I'm never going to use the fact that you have equality in the other direction. Right? So I'm only going to use the fact that this is a consequence of this. I'm never going to use equivalence. So if you are not happy with that, it's fine. Okay, maybe a simple example just to see how good this bond is. Oh, yes, maybe before that I should. There's been a lot of work on this curvature, and in particular, it's very surprising, but you can also say interesting thing about the mixing time when k is equal to 0. This formula becomes useless when k is equal to 0. So you can still have a mixing time bond. It's the argument looks roughly the same as for this, but at some point you have to differ from it. And you get this nice bond. So there is a constant which is universal, and then times d times the diameter square. Okay. I'm not going to use it, but just to mention that even when the curvature is non-negative, it's interesting. You don't really need a positive bond to get anything useful. Okay, and this parameter d, it's the one we have already seen. It's the 1 over the... Right, this is the sparsity parameter, so maximum over all neighbors of 1 over txy. Okay? Okay, so let's see a bit on our toy models how those notions look like. Just to see if those bonds are good or not. Okay, so you start from a point x, you start from another point y, you run your dynamics. So in my picture in the Riemannian geometry, you have those two trajectories, the yellow and the red. Here they are random, they are just realization of my Markov chain. Right? So this one does something like that. And you would like to couple this with the trajectory starting there in such a way that the distance on average is as small as possible, hopefully decreasing with time. Right? That's how you get a bond on the curvature. It's something very concrete where you just need to couple trajectories and look at the distance between the points. How does this evolve in time? Right? So what can you do on a cycle? One stupid coupling is, whenever this one moves clockwise, this one also does. And same when this one moves backwards or anti-clockwise, this one also does. If you do that, then of course the distance will remain constant between the points. Right? So you know that the curvature is I mean, you have this statement with k is equal to 0. Maybe you could do better, but at least you have this. Right? So this stupid coupling already shows that the curvature is not negative. Right? In fact, you cannot hope for better just because you know, in any coupling, there is equality here because in any coupling, right? This was one particular coupling, but so maybe you could come up with something better, but in fact, no. In any coupling, you will have this that say you want to understand the distance between xt and yt, but certainly this distance is at least, and this will be larger than the distance like that. And those are, now you don't have any coupling, right? It's marginal distributions, and those are martingale, right? So they, on average, they remain where they are, right? So this is constant. It does not depend on time. Okay, so you see that, in fact, you cannot hope for, I mean, in any coupling, the distance has to, cannot decrease, right? It has to remain constant or increase. And there is one coupling where it remains constant. So in fact, there is equality. So the curvature, the cycle is a flat manifold, if you want, in the discrete one. Same argument would work for the torus in any dimension. Okay, so what do we get in terms of mixing times? Right, we cannot apply this estimate. This is for positive curvature, but we still have this one. And so what we get is that, so the degree here is the number of, the degree is really, when you have simple random walks, this parameter d is really the maximum degree in your graph. The degree is 2, right? So it's just a constant. And so what you get is n squared. You get that T mix of epsilon is just a constant times n squared, which is the right order of magnitude, right? So it's already much better than what we did before with Poincaré and with even modified log Sobolev. And that's one of the nice things with curvature. It's very easy to study, right? Computing the modified log Sobolev constant of a Markov chain is difficult. Estimating this curvature k is very easy. It's coupling. You just come up with a good coupling, and that's it. Okay. And you see the bond is already very sharp. Okay, so let's look at example 2 now. So random walk on the n cube. So remember, in this n cube, you have n coordinates minus 1, 1. And whenever you clock rings, you choose one of the coordinates uniformly at random and you flip it. Okay. So each coordinate flips independently at rate 1 over n. Right? Okay, so that's just a reminder of what this Markov chain is. But I'm going to rephrase this in a slightly different way. Each coordinate, instead of being flipped, so changing minus 1 to plus 1 or plus 1 to minus 1, I'm going to double the rate of my Poisson clock. And whenever it rings, I refresh my random variable uniformly. Gets refreshed independently at rate twice what it was before. Right? And by getting refreshed, I mean you replace the value of that coordinate by a uniform minus 1 or plus 1. Okay? And that's the same, right? Just by the Poisson property. I mean, flipping at rate 1 is the same as refreshing at rate 2. Okay? Yes? Where they get closer, you mean like that?
They end up becoming equal.
No. No, because you have to, I mean, if this, you can say when this one goes like that, then this one goes like that. But then it means that when this one goes there, then this one goes there. And so if they were very close, now they start to. Right? So no, you cannot gain. You cannot beat this this martingale property. Okay, so everyone agrees with this equivalence? The same thing? And then, now that you have this formulation, it becomes easy to couple two trajectories. You use the same clocks and the same refreshing values. So it's a completely trivial coupling. In the obvious way, it's called parallel coupling. This was also a parallel coupling. The same clocks and same values for refreshment. Not sure this is a proper English, but you see what I mean. Okay, so whenever my clock ring, in my two chain, I'm going to replace the corresponding value by exactly the same new value. So this way, I cannot create any discrepancy, any new discrepancy between the coordinates, right? Whenever I modify the chain, now my two trajectories, they agree a bit more than before. Okay, so the distance is actually non-increasing in this, with this coupling. Okay, again, it's a particular choice. It's maybe not the optimal one. You'll see that, in fact, it's optimal. But that's a very natural coupling to try. You try to erase the discrepancies as much as possible. And so you see that if you look at under this coupling, if you look at the expected distance at any time t, starting from any two initial locations, well, once a bit has been refreshed, when the clock associated to a coordinate has rung, you know that the two coordinates will be equal, and they will remain equal forever. Okay, so this is just, in general, it's just expectation of, by definition of my distance, it's really this indicator that xt I is different from yt I. Right, that's my Hamming distance. And then this is the same as saying that my ith coordinate didn't ring so far. So it's the same as probability that, or maybe I should write it like that. So first of all, if they were equal initially, they remain equal, and if they were different. So this is the initial value, x0 and y0. And then the probability that my clock didn't ring for this one is exponential of minus 2tn, because the clock rings at rate 2 over n. Right? So, okay, so this is exactly the initial distance times this. And so you see that the curvature here, this coupling shows that the curvature is at least 2 over n. Okay, can you come up with a better coupling than that? No, as you will see. But first, with this coupling, what bounds do you get on the mixing time? So 1 over k becomes n over 2. And then you get log of what's the diameter of this hypercube? How far can you get from, how far can 2 points be on the hypercube? N. What was the mixing time of the hypercube? N log n, so it's very good. And again, the argument is much simpler than what we did before, right? Much simpler than estimating the modified log Sobolev constant. So it's almost sharp. You would need a 4 here to be sharp. Okay, so it's very good. So maybe you can find a coupling for which instead of 2 you get 4, and then you would get cutoff. Okay, let's see what you get in terms of the spectral gap, because there is also this nice thing here. My chain is reversible, so this inequality I can replace lambda by the spectral gap, gamma. And this coupling shows that gamma is at least 2 over n. Do you remember what was the spectral gap for this chain? It was exactly 2 over n. So this shows that this is sharp, and even more, this shows that you cannot get a 4. You cannot improve this. Otherwise, you would violate this. Right? There is equality. We have seen by computing eigenvalues that this is actually not only a lower bound, it's really an equality. Okay, so it's a pretty easy to apply theory, and we are going to do that maybe a bit later if I have time, but you should really think of this curvature as something that, unlike the Poincaré or modified log-Sobolev inequality, something you can apply to concrete Markov chains. Right? So you can compute the curvature or estimate the curvature even for Monte Carlo Markov chain algorithms. Right? So if you look at the Ising model on any graph, you get an estimate on the curvature very easily. It's just coupling, so it's very easy. So in my opinion, it's a very successful theory for studying mixing time.
So why you call it curvature? It's just coupling, no? You use coupling.
So yeah, I totally agree. So this was, of course, invented before curvature. You didn't need Yann Olivier. This was called by people in Markov chain just path coupling. Right? My point is that there is much more into it. That what I would say is that path coupling is the application of curvature to mixing times. So it's what I presented. But as you will see, I'm not going to use this for cutoff. I'm going to use another viewpoint on curvature, which is really the differential geometry viewpoint. And this is even more useful for Markov chains. Okay, so adopting this general view, this general Riemannian analogy to path coupling, really makes this method much more interesting than just a method to get bonds on mixing times. Okay, so you'll see that. We'll get much more out of it. Okay, it's only, so before that it was just a method to bond mixing times, and when Olivier came up with this relation between this notion of path coupling and the Riemannian geometry of curvature, he came up with all those conjectures about whatever is true in the Riemannian geometry setting and should be true also for Markov chains, and this generated a lot of new work that you would never have obtained without this viewpoint. Right? So, and one of them is what I'm going to present now, this Perez-Tetali conjecture. It's much more than path coupling. Okay, but maybe before that, so you can argue that those are simple examples where you can compute things easily. There is a nice result, an important result, which tells you that in fact you don't really need to study couplings in a very complicated way, because curvature is local. This lemma tells you that the following conditions are equivalent. So the first is, of course, maybe the last one is the one we really want, which is this very strong, the definition of curvature. Right? So. Right, this is what you want to prove in order to claim that you know the curvature of your chain. And it looks like a complicated thing to do, but it's the same for Poincaré and modified log-Sobolev. In fact, you never actually prove exponential decay. You prove an infinitesimal version of that at time 0 when you differentiate, and this is much easier. It's a static condition, so you have the same here. But the first good news is that this is for every mu and nu. In fact, it's enough to look at mu and nu that are Dirac masses, and even Dirac masses at neighboring points. So it's enough to have this at Dirac masses, and also it's enough to work in discrete time. Okay, so let me now formulate the general thing. So it's enough to understand Wasserstein distance between. Okay, maybe I'm going to do it in continuous time first. So it's enough to establish this inequality for Dirac masses. that this should be less than the initial value, which is just really the original distance. And you get a k. Excuse me?
The last one is an
Inequality, sorry. And this is the same. I can even remove distance because I can restrict myself to neighbors. Right? So if you can prove this inequality for Dirac masses at neighboring states, that's enough. That's already a good news. So we didn't really need to look at all possible initial conditions. Just start at neighbors and try to couple so that it works. And also, you don't need to look at any time t, but only at infinitesimal times by the Markov property. So in fact, it's enough to do this in discrete time, starting from any two neighbors. Right? So the only thing you need to prove is this. So in discrete time, this exponential decay becomes just a geometric decay. So that's it for every x neighbor. Right? This is a very simple condition to check. What it means is that if you want to study curvature, you just take two neighboring points in your state space, so 2 points that are connected by an edge, and you try to couple one step, one transition starting from x and one transition starting from y in such a way that the expected distance is as small as you can. Right? And that would be the same as doing this very complicated thing. Okay, so it makes it a very tractable property to check in practice. Okay, it's an easy statement. You can look up in the notes. It's basically just the triangle inequality and convexity. It's very easy, but in my opinion, it's the reason why curvature is so successful. That you have this local way of checking something that is global and at any scale, it's enough to check it locally. Curvature is very much, it's often compared to convexity. Right? Convexity is something that is, you can check, I mean, once you have convexity, local information gives you global information about functions. This is the same. You have this local information and it gives you something amazing about mixing times, for example. Yes?
Random walk on a graph, if you have two neighbors which have no common neighbor, then it's not possible.
Exactly. So that's yeah. Maybe I should give you an example of a negatively curved chain. Ah, yes. No, I see what you mean. So I'm cheating a bit here. So those are really equivalent. This is an implication, and it's the one we really use because we want a simple criterion to imply a complicated one. If you want to reverse this, you actually need laziness, but laziness, you can always assume it for free. So this requires laziness, which means that you have a chance 1/2 to stay where you are. But if your chain is not like that, you replace it by you replace t by t plus identity over 2. And in terms of semi-group, it will just rescale time by a factor 2. So if you care about exponential decays and things like that, if you can get exponential decay for the lazy version, you get it for the original one as well. Right, so it's not a big deal, but you can, without loss of generality, you can always assume this, and then you really have this equivalence. You're right. Okay, sometimes it's better to stay where you are if you want to couple the chains. Okay. But anyway, in practice, this is used in the other direction. You check this in order to get this. Okay, maybe a counter-example, I mean, an example of a negatively curved chain. Just out of curiosity, we're not going to use that, but. Right, the nice thing is that this is a local property. If you want to determine the curvature, all you need to know is you just need to know, you take an edge and you want to know the ball of radius 2 around that edge. That's enough to determine the curvature of the chain. Okay, so if you want the curvature to be negative, you want that when you make one step starting from x and one starting from y, the outputs that you get are further away than what they were before. So it's easy to cook up an example like that. Just look at a random walk on a tree, on a finite tree, for example. Right? As soon as in your chain you have something like that, then it's clear that when you make one step starting from x, there is a strong drift in this direction, and one step starting from y, the drift is in this direction. So there is no way that you can couple them so that on average the expected distance decreases. Right? So typically random walk on trees are negatively curved. a more interesting example, trees are not so interesting, but if you look at random walk on an expander graph, so those are very, very useful in practice, and people would really like to understand cutoff for expanders, then any expander will have this property that, on average, the distance grows with time. Okay, so expanders are in this world. The analog of hyperbolic manifold in the discrete are expander graphs. And so they are, that's just to say that there are interesting chains which are not on this side of the world. Maybe as a spoiler for what we are going to do in the last two lectures, the goal of this curvature theory for us will be to get a theory of cutoff. So we'll get a nice understanding of cutoff on this part. On this part, cutoff will be understood. Right, so here and here you will have simple criteria to deduce cutoff. But in this part of the world, I don't know how, I don't have any theory. And there is this interesting class of examples where it would be very interesting to get a theory. Okay, so that works for you guys. As you will see, most of the tools, I mean, many of the tools that I'm going to use for my cutoff theory will apply to both worlds, but at some point I will use specifically this positive curvature. And so you have to find an alternative argument there in order to make the theory work there. And that's open problems for you. Okay, just a motivation for later. Okay, so let me move now to an interesting connection between curvature and what we did before, so entropy. It's called the Perez-Tetali conjecture. Just like the product condition, it's a conjecture that ended up to be false, but it was even more interesting. The fact that it was false was even more interesting because it generated a lot of interesting work. Okay. So we have this curvature quantity, this optimal curvature, K. And this has many similar, it shares many similarities with this modified log Sobolev parameter that we studied in the past lectures. Similarities with this modified log Sobolev constant. Okay, at least formally, you know, the both control the exponential decay of variations of functions. Right? Remember, this alpha optimum quantifies the exponential decay of the entropy of F along the semigroup. And this one controls the exponential decay of Lipschitz norm of F. But Lipschitz and entropy are both ways to quantify how much F varies, how far from being constant F is. So from that point of view, they are very similar. Right? So both control the Poincaré constant. Right. And also, one thing that we saw for alpha, but we did not see it for K, but it's actually true, both imply sub-Gaussian concentration. Right. The sub-Gaussian concentration estimate that I gave you was involving this parameter alpha. It's also true with the parameter K. Okay, so when you see this, and when you look also at particular models where we can compute alpha, you realize that in most of the cases they are of the same order. And so Perez-Tetali conjecture is the conjecture that they are actually the same thing, or that they are related. So it's attributed to Perez-Tetali, but when you ask them, they say that they never say that. But there are many papers citing this Perez-Tetali conjecture. There's been a lot of work on that. So the conjecture is that if you know the curvature, you control this modified log Sobolev constant. So So I like to put it in this way that it controls entropy. So the precise statement is that if you know a bound on the curvature, then you get a bound on this modified log Sobolev constant. Maybe up to constant, they were not as bold. Anyway, they never stated this conjecture, but up to universal constant. So it's not really true that they never stated it. It was really something that came up in the community. People refer to it a lot as Perez-Tetali conjecture. But what is true is that I know the two persons, and I went to ask them if they believed in the conjecture, and each one of them told me that it was the other guy who actually conjectured it. So, yes. Okay, so one thing is that this would be very good news, because remember, this is a very strong quantity. It controls many nice things. It's important to have bonds on it, but it's difficult. The modified log Sobolev constant, one thing you should remember from the course is that it's something that is very not tractable. Right? Whereas this, I hope to have convinced you using basic examples that this is easy to compute. It's just couplings. So having this relation would be very nice. It would make this entropic world much more tractable in a sense. Okay, so unfortunately, this is not true. So there exists counterexample. And actually, the counterexamples are rather simple. So this is due to Florentin Munch. But it's very recent. He realized this in 22, I think, or 23. Maybe even more. He's not a probabilist, he's a discrete geometer. And it's embarrassing because the counterexample is just a Markov chain on free states, right? So it's a birth and death chain on free states. There is a parameter. Right? All the rates are chosen so that you have a very large chance to stay where you are at 0. So when epsilon tends to 0, the mass here becomes larger and larger, and then you cook up the weights here so that you have a positive curvature uniformly bounded away from 0 independently of epsilon, but this tends to 0 with epsilon. So no way to get any statement. Okay, so that's bad news. But the good news is that you can repair the conjecture by looking at reasonable chains, as usual. So it's true for reasonable chains. Any conjecture, you can repair it like that. Okay, so to formalize this, I will need to strengthen a bit this notion of curvature. So I defined this W1, so let me repeat the definition. Was the infimum over all possible coupling, and then you look at expected distance. And there was this parameter 1 here, and you can play with this one. You can put a p instead, or any p. So the p Wasserstein distance, you just raise this to the power p, and then put 1 over p. Right, so that's a nice distance between probability measures. So you can play the same game as before, study how this evolves under the semigroup, and you come up with a definition of curvature, but now with this parameter p. Right? Right, such that Wp is decreasing at an exponential rate. For every mu nu and for every time. Okay, it's just the same thing as before, but with this p instead of p equal 1.
There is a p missing.
Yes. Thanks. Okay, and again, you have this nice characterization. Everything that I stated for curvature remains true. So this theorem remains true with P. Maybe I should use different colors, but this remains true, this nice characterization. It's enough to look at what happens at any age. Right. So in particular, with this notion, it's clear now, because this quantity is increasing with P, right? By Jensen, this is increasing with P. And now you see you want this to be small after one step when you start from neighbor. So you see that the larger P, the harder this gate. Right? So from this inequality, you get that Kp is decreasing with P. Okay, so pretty much the same theory works as before. And now here is the repaired Perez-Tetali conjecture. It's essentially due to Florentine Munch, but then we realized with Pietro Caputo that we could go a bit further. So the statement I'm going to give is a joint work between the three of us. So it's the repaired Perez-Tetali. So the Perez-Tetali would be this, that alpha optimum is larger than K1. And now we have to add a bit something that could be negative here. And this is K infinity, but K infinity of the adjoint. So it's the P equals infinity curvature of the adjoint semigroup, PT star. Okay, if you don't like this, just think of a reversible chain, and this is just K infinity. Okay, so it seems that this is even stronger than this. Right? But remember that this could be negative. In many cases, this is negative, and then you don't get the percentage. Okay, so what does it mean? You know, that it's true for reasonable chains, where reasonable here are chains for which this is non-negative. Okay, so in particular, when you have this nice K infinity star non-negative, we recover the original Perez-Tetali conjecture. And as we'll see, many chains have this property. And so that explains why Perez-Tetali did this mistake of thinking that this is always true. In most of the models where you can check those quantities, this was satisfied, and so indeed you had this larger than this. Okay?
Is it optimal?
Good question. I would really like to have, instead of this, I would like to have K2 and K2 star for certain reasons, and I cannot make it work. But you'll see that in certain examples, this is really at least up to a universal constant the right thing. So let me, maybe before I prove this result, let me illustrate it with a few examples, also from the world of diffusions, because this is interesting to most of you, I guess. Okay, but again, the take-home message is that this quantity is difficult to estimate in practice, this modified log Sobolev inequality, and this gives you a very tractable coupling-based way to compute this. So in particular, from this, we'll see that you get the modified log Sobolev constant up to universal prefactors for Glauber dynamics on your favorite spin system, which is a chain that is difficult, right? And then, yes, so it's a very useful result, I would say. Okay, so maybe just example. Maybe the n cube. By the way, the two coupling we saw, the one for the n cycle and the one for the n cube, both of them had this property that not only the distance decreases on average, but it's non-increasing almost surely. Right? For the cycle, we did this. For the cycle, it was this, whenever one moves clockwise, the other one moves clockwise. This has the property that almost surely the distance is non-increasing, which means precisely this. Right? Because proving this, what does it mean, proving this? Maybe if you take p is equal to infinity, what you want to prove is that the L infinity norm, which is just the maximum value of this distance, is at most what you started with. Right? So proving k infinity non-negative really means that you can couple one step starting from x, one step starting from a neighbor of x, such that the distance is almost surely at most what you started with. Okay? And this is the case for our coupling on the cycle, and this is also the case for our coupling for the n cube. Okay? For the n cube, we make sure that we don't create any new discrepancy between the two trajectories, so it has this nice property. So our coupling the same as before. K infinity is non-negative, and K1 was actually like that. Right? Our coupling shows this, but then I argued that this was optimal. And so what you get from this is that this optimal log Sobolev constant is at least 2 over n. Okay? Do you remember the exact value of this alpha opt? I never computed it because the computation is quite hard. But it's 4 over n. Right? And it's quite involved computations to prove it. Here you get it for free. Okay, maybe an example that is more convincing to you because you don't care about the discrete world. Let's look at diffusion. Yes? Okay. In this case, this is in the discrete you cannot hope for better than 0. No, I meant K2 plus K2 star. Ah, yes, 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 right. Like exactly. So that's one of the motivations. Exactly. Yeah, good remark. So that's why I would really like to have K2 plus K2 star. Then you would really get the optimal, the right modified log Sobolev. Okay, so example 2 is diffusions. So Langevin diffusion in a convex potential. So remember, we have already seen that. So it's look at this differential equation. This is d, gradient of u of xt dt plus square root of 2 dbt. And u, we are going to assume that u is a convex. The Hessian of u is at least rho times the identity for some rho strictly positive. Okay, so you look at this Langevin diffusion in a convex potential. Okay, and I would like to apply this theorem. So for this, I need an estimate on the curvature. So to estimate curvature, I need coupling. So how would you couple two diffusions like that, starting from different points? Okay? So I have this, and I have another diffusion with the same, following the same dynamics, but starting from a different initialization, and I want to look at the distance between them. And what I'm going to do, you see I'm using the same letter here. I'm going to use this parallel coupling where I use the same Brownian motion for both. You could do anything else, right? There are several ways to couple those dynamics, but let's take the trivial one where you use the same Brownian motion. And you see that when you look at the difference, this noise part cancels out. Okay? Right. When you use this parallel coupling, you get this. Of yt dt. Okay, and therefore, when you look at the distance, right? You differentiate this, you get twice the scalar product between this and itself. And so using this formula, you get that it's gradient of u of xt minus gradient of u of yt, scalar with xt minus yt dt. And then you use convexity to say that this is at most. Right? Our convexity assumption on u give you a bound on this. Right? So it's at most minus 2 rho times xt minus yt square. Okay, so you get a differential inequality for this. And there is dt everywhere. And so from this, you get exponential decay. So there is a square, and it's at most exponential of this, so the 2 cancels out, and you get this. Okay? I'm sure you have seen this, this property. You see, this is almost sure. Right? We got rid of the noise here, so everything becomes deterministic. This is an almost sure statement. So it tells you that this k infinity here is at least rho. And of course, k infinity is at least k1, so from this you also get that k1 is at least rho. Right? And from this you deduce that the modified log Sobolev constant, so if you want to look at the entropy of this Langevin diffusion, the entropy has to decay exponentially fast with a rate that is 2 rho. Okay? And moreover, we are in this diffusion setting where once you understand the modified log Sobolev constant, you actually understand the log Sobolev constant, so hypercontractivity. So you can even upgrade this for free to something about hypercontractivity. You lose a factor 4, so you get this. Right? And so Massimiliano, he was asking if this was sharp. This is a well-known result, and it's actually an equality for Ornstein-Uhlenbeck. So it's the right constant. Sharp for Ornstein-Uhlenbeck, so for when u of x is x squared over 2. Okay, so this is not new. This the fact that when you look at Langevin diffusion, the log Sobolev constant is at least the convexity of Eurasian. This is a famous theorem, a famous outcome of this Bakry-Emery theory of curvature. I just wanted to show that you can also recover it from this Olivier-Ricci theory of curvature. So that's a nice application of this example. Okay, so in the last few minutes or 20 minutes, let me try to prove this theorem, because here you will see again certain ingredients that will be useful later. Are there any questions?
Are there any qualities where there is P and you kind of move P?
Yeah.
This is kind of duality.
Yes, yes. So that's why I was mentioning the K2, K2 star, and maybe KP and KQ star. Exactly. It makes sense. I've tried, I've failed, but you'll see the proof of this is easy. So you'll see that maybe. Yeah. Okay. Okay, so I'm going to keep the theorem maybe and look at the proof. So the strategy will be, so the reason why this Perez-Tetali conjecture remained open for a long time is that, even though they look like similar things, it's very difficult in practice to relate entropy and curvature. One is geometric, the other is purely information theoretic. There is no reason a priori that they have to talk to each other. Also, maybe I should mention one important point in this theorem is that it's true for any metric. You choose your favorite metric dist on the state space. For this metric, you compute those numbers, and this gives you a bound on this, which this has nothing to do with the metric, right? It's modified. So I wrote it for this specific distance, but you will see in the proof, you can make, and this becomes a nice optimization problem where in order to get a good bound on alpha opt, you try to optimize the metric so that you get good contraction properties. And sometimes the right metric to use is not the one given by your chain, but some clever. So I have examples of that. Okay, so this makes the theorem even more surprising. That whatever the geometry you put on your state space, this gives you a bound on a control on the entropy. Okay, so the starting observation. So we have already seen that or dual expressions. We have already seen that if you control the K1 curvature, then you control the Lipschitz norm. Right? So that's another way to view curvature, just by duality. Okay, and the proof is very easy. And now there is a similar version of this for the K infinity curvature. It's just a nonlinear version of this where you control the Lipschitz norm of the log. Right. If you want to control this in this slightly stronger sense, then what you need is the infinity curvature. Okay, so let me prove this. So it's for any time t, so I can fix time and forget about it, and then.
You have the middle ones or no?
Ah, good question. I don't know. Good question. Yes, yes. For the K2 and K2 star, you would need that. Yeah. There is something magic about those two cases, so yeah, we'll see. Okay, maybe let me start with this one. Even though it's a consequence of duality, I never proved to you this duality formula. So let me just to see how it works, just prove this. You'll see that it's really easy. So you fix time and you let x, y be distributed as an optimal coupling. And now I have to be precise. It's a W1 optimal, right? One which realizes the definition of this W1 curvature. Optimal coupling of PT starting from x and PT starting from y. Okay, and t is fixed here. It's nothing dynamic, right? You fix t. You want to prove this for a fixed time t. So I take a coupling that realizes W1. So what does it mean that it's optimal? It means that when you compute the expected distance between x and y, you get exactly this Wasserstein distance between the two measures. So it's one that realizes this. And so in particular, using the definition of curvature, we know that this is at most K1t times the distance. Okay, so that's what we know about this coupling. We know that there is a coupling like that. And now I can use it as follows in a stupid way. That if you want to compute PTF of x, this is just the expectation starting from x of f of xt. And same for PTY. Maybe I forget about the x, yt. Right? Xt and yt have those distributions. It's a coupling, so okay. So maybe I can use x and y instead of xt and yt because x and y have the right distributions. Right? And so now I look at the difference. And because they are coupled, I can put this difference under the same expectation. It's really this. So Massimiliano argued that there is only one result in probability, one tool in probability, it's Fubini. I would add another one, it's just Jensen. Right? You just, whenever you see absolute values outside an integral, just bring them inside. This will lead you very far. Okay, but that's exactly because f is Lipschitz. That's at most the Lipschitz norm of f times the distance. And so it's at most this. times the distance between the initial points. Now you see the inequality that we get a bound on the Lipschitz norm of PTF, because we know how much different they can be in terms of the distance between the points. So what we proved is that the Lipschitz norm of PTF is at most this constant here. Okay, so that proves this. Okay, you just use the coupling in the obvious way. This curvature gives you a coupling, and you use this coupling to get an estimate on the Lipschitz norm. Okay, so let's do the same for this version now. So that was the proof of this first inequality. And now I'm going to prove the second one. Same idea. So again, xy is an optimal coupling, but now W infinity optimal. Coupling of my two distributions, so PTX and PTY. And so what I know is that almost surely now the distance between x and y is at most this optimal value. And this, by definition of this k infinity curvature, is at most times this. Okay, so far it's exactly the same argument as here, but with WP instead of W1. Okay, so W infinity gives you a control almost surely, right? It gives you a control on the L infinity norm, which is almost sure. Okay, and now I'm going to use the Lipschitz exactly as I did here, but I have a control on the Lipschitz norm of log f, not f. So let's look at log f. So log f of x minus log f of y will be at most the Lipschitz norm of log f times the distance. And the distance is given by this, so I get this. Right? Okay, now I'm replacing the log, I'm taking exponentials. And you get that f of x is at most f of y times the exponential of all of this. Right? And this is this. Okay, so just taking exponential. But remember that, and now I take expectations. This is deterministic. So I take expectations. Right? As I did before, actually. Right? These expectations were precisely the quantity I'm interested in. So take expectations. And then take log again. Right? We took exponential, then expectations, now we take logs. Right? Remember that this is just PTFX, and this is just PTFY. And when you take log, you get a bound on the log Lipschitz norm of log P, on the Lipschitz norm of log PTF. You get this one. Right, so what you obtain in the end is that the log of PTFX is at most the log of PTXY plus the constant that was there, which is still the same quantity here, this one. But this is true for every x and y, and so you get a control on the Lipschitz norm. So you get a control on the Lipschitz norm of log of PTF in terms of what was there. So it was the Lipschitz norm of log f, and then times the exponential of minus k infinity. Okay, so that's a proof of this. Okay, so it's very easy. There is nothing deep here. And now I can prove the theorem in one line. I will just need this lemma that we have actually already seen in the log Sobolev case. So that's the key lemma. It's the modified log-Sobolev version of it. Right? So if the infimum in this modified log-Sobolev constant, what you want to understand is this. Maybe I can call it rho. It's the infimum of, or it's actually the supremum. Sorry, supremum. What you want to understand the entropy of PTF star. We'd like to say that this is at most an exponential minus something times the entropy at time 0. Right? So you want to understand this constant. And if this is achieved by so the supremum is over all non-constant. If this is achieved, then you have a particular equation solved by the extremizer. Then you solve this, the fact that the gradient of the functional at f must be 0, and you get an equation exactly as we did for log Sobolev. And here is the equation that you get. Simple differential calculus, and you get this. So we get that pt of log of pt star of f must be equal to rho times log of f. Okay, it's one of those stupid pointwise equations that you get when you solve this minimization problem. Look at the gradient condition for it, the Euler-Lagrange condition, as Massimiliano said. Okay, why is it interesting? What's the connection between this? So this is a trivial lemma. Right? It's just basic calculus. Why does this give the Perez-Tetali conjecture? Well, take the Lipschitz norm on both sides. Right, so you get on this side you get that it's rho times the Lipschitz norm of log f, and this has to be equal to the Lipschitz norm of this. So pt log pt star f. Right? And now I'm going to use the dual formulation of curvature. So dual formulation of k1 to say that this is at most exponential minus k1t times the Lipschitz norm of log pt star f. Right? And then I'm going to use the dual form for k infinity. And I know that this is at most this times this infinity, but you see apply to the adjoint. And then Lipschitz log f. Okay? And then you simplify by Lipschitz log f, and that's it. Okay? So it's a bit like in the log Sobolev argument. You know, when we wanted to upgrade modified log Sobolev to log Sobolev, this has been open for a long time because people were trying to prove log Sobolev. In this log Sobolev equality, there is a for every function f. It's quite difficult to try to actually prove this functional inequality for every f. But the key to both conjectures actually was the fact that in fact you only need to work with the extremizer. There is one function that you really need to look at. And this function satisfies an S equation. And from that you get the conjecture for free. Okay? So very simple argument in the end. Okay, so next time we move to Bakry-Emery curvature, and with that we can finally understand cutoff, at least on this side of the world. Any question? Yes?
Is there a way to see the curvature of the chains with the graph that you see?
Well, yes, it's this picture that, so it's essentially this picture. It's a local property of your graph in the sense that you have to check in every ball of radius 2 that you see. You just need to understand the neighbors of x, the neighbors of y, and how they are connected to each other. And yeah, you You want something that is, you want that when x and y are neighbors, there are many common neighbors or something like that, right? Yes? Yes, so that would be close to the picture I drew where you had this tree thing. Right? Something like that as negative k. Right? Yes.
Can curvature depend on the number of points in the? I have a specific example in mind. So for example, we are in a ball, and initially we are at curvature 0. So we have a map on the ball that's very close to the square, and then the square increases with the number of points in the Markov curve. So is it allowed for the curvature to change?
Okay, I'm not sure I understood the question, but if the question is about, you have this Riemannian notion of curvature for manifold. Now you can discretize your manifold, look at this discrete version, and let the step tend to 0. Yes, so this has been done. This shows that you can recover the curvature, the original notion of curvature on your Riemannian manifold by taking a limiting procedure. So this is explained in the survey by Yann Olivier. Because when he introduced this discrete notion of curvature, he needed to convince people that it's actually the right analog of this. And so he has this argument.